I'm going to define a few functions here. First function I'm going to define is little f of t. And I'm going to define this to be a continuous function over the interval from a to x. Next thing I'm going to do is define a function capital F of x to be the integral from a to x of little f of t dt. And from a to x, that's the interval where my little f is continuous. And another function I'm going to define is g of x. I'm going to define this to be an antiderivative of little f of x. And I'm going to take a look at this right here. And I'm going to take the derivative on both sides. So, derivative of capital F of x is capital F prime of x. And to take the derivative on the right-hand side, well, the fundamental theorem of calculus part 1 tells me that I can just take this x right here, my upper limit, and plug it in right here. So the derivative on the right-hand side will be little f of x. Now, what does this mean? G of x to be an antiderivative of f of x. Well, that means that if I take the derivative of g of x, I will get little f of x. Notice that the same thing is true here for capital F of x. If I take the derivative of capital F of x, I will get little f of x. So that tells me that capital F of x is also an antiderivative of little f of x. So I have g of x and capital F of x are both antiderivatives of little f of x. Now, does that mean that g of x and capital F of x are the same? No, it does not. If you have two functions with the same derivative, that means that they're either the same or they are off by a constant, because the derivative of any constant term is just 0. So what I can do is relate these by saying capital F of x equals g of x plus some constant, where I'm going to use a capital C to represent constant. Now, what is capital F of x? Well, it's this function right here. So I'm going to write this down over here. The integral from a to x of f of t dt, little f of t dt. Remember, that's my capital F of x. So this has to be equal to this right here. G of x plus some constant. And this equation has to be true for all values of x. So to solve for c, I'm going to pick a value of x. I'm going to pick x to be equal to a. And why would I want to do that? Well, if I plug an a in right here, when I have the integral from a to a, that's just 0. Because there is no area between a and a. It's just like one point. It has no area. So when I plug in x equals a in here, on the left-hand side I'm going to get 0. And on the right-hand side I'm going to get g of a and plus c. So if you subtract g of a on both sides, that tells me that c is equal to negative g of a. So I can plug that in now right here. So I can replace this plus c right here with minus g of a. Should make it clear that that's an a and not an x. So let's focus on this equation right here. So what does this mean? Well, we know that g is an antiderivative of little f. So let's look at what I've done here. So I have the integral from a to x of little f of t dt, and I found out that this is equal to an antiderivative of little f evaluated at the upper limit of integration minus the same antiderivative of little f evaluated at the lower limit of integration. So I can use this formula right here to solve any definite integral that's continuous over the interval we're trying to integrate. So this is how we usually write it. We usually change the variables up a little bit, but it's still the same thing in the end. As soon as this works. So the fundamental theorem of calculus part 2 states that if we have a continuous function that we're integrating over this interval right here from a to b, a and b are just any two numbers, then what we have to do is find an antiderivative and evaluate it at the upper limit of integration. And then we have to subtract the same antiderivative evaluated at the lower limit of integration. Remember, it doesn't matter which antiderivative you're using because they're all off by a constant. And as long as you use the same antiderivative both times, when you subtract them, the constants will cancel out. So you'll wind up with the same result in the end.